So today in this class, we are going to basically discuss few of the problems that I have already given to my students. So those who are looking at this video maybe for the first time, for them I am sharing the problems. So please take a screenshot of these problems, and today I'm going to discuss or solve these problems. So the students have already given a half an hour exam, and hopefully they did quite well on that. But let us first have a look at the questions. The questions are very easy since it's just an introductory course and almost at the very beginning of the course. So may I request all of you, those who are looking at this videos, to have a screenshot of this question so that during the session when we require, we'll able to solve this. So the first question is, find the order of the element 92 in the group U101. Okay, so that's my first question. The second question is, find the order of the element 1, 2, 3 dot dot 50 to the power 8 in the symmetric group 8S101. Okay, so let me first go to the second question. Let us first have a look at the second question, which would be easier to solve. So we are actually trying to find the order of the element 1, 2 dot 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 50 to the power 8 in the symmetric group S101. Okay. So to solve this problem, we are going to use a simple formula. The formula is, let G be a group, and let A belongs to G, be an element of G. Let order of A equal to n. Then for any positive integer, then for any positive integer t, the order of A to the power t is how much? So that's very important. So this formula will be very much useful for many of the competitive exams, and this is nothing but order of A divided by GCD of order of A comma t. Okay, so as here order of A is n, so it will be n divided by GCD of n comma t. Okay, so to prove this, I am not going to give you the formal proof of this, but to prove this result, you will be certainly required few of the interesting things like well ordering principle. I mean, I am giving you the whole idea of the proofs, and while you will be doing the proofs, then you will require few of the results to prove some results that will be required to prove this result. So out of this result, few of the interesting important results are well ordering principle. Can somebody tell me what is well ordering principle? What is well ordering principle? Can somebody tell me? So it says that S, if S is a, sorry, it says that, so the well ordering principle says that if S is a non-empty subset of, so it should not be empty, non-empty subset of the set of natural numbers, then S must contain a least element, must contain a least element. What does it mean? If you take any non-empty subset of the set of natural numbers, then it will have a least element. Tell me any subset non-empty set S equal to, say, all even integers, positive even integers, 2n, such that n belongs to n. Then certainly this will be a subset of n. Okay, and you can see that 2 is the least element of S. So that is the idea of principle, well ordering principle, and I am sure that in your first course of undergraduate level for classical algebra, you must have did all those things. So that's the principle, well ordering principle. So another very important result that will be required is that let GCD of A and B, where A, B are two integers, be D. Okay. Then there exists U and V belongs to Z such that AU plus BV equal to D. Okay. What it says that if GCD of AB is D, note that when I am talking about GCD, so at least not all of them are zero. So at least one of AB is non-zero. So not both are zero. Okay. So when I'm talking about GCD, what I'm saying that at least one of AB must be non-zero. And if D is the GCD, then there exist integers U and V such that AU plus BV equal to D. Now my question is the converse true? That means if you have D, suppose if you can write D as a combination of some U and V of A and B, then will you be able to claim that this D is the GCD of this? So question that you need to think about, it's a homework. Is the converse true? Is the converse true? That means if you are given some UV and AB and D, and if this relation is satisfied, will you be able to tell that D is the GCD of A and B? Is it true? What is your intuition? True or false? What is your intuition? Any guess or any idea? Okay. So if not, it will be like your homework. Okay. So
False.
okay, can you give me some example? Somebody says it's false. Okay. Now please give me some example where you can write D in terms of AU plus VB, and then D will not be a GCD of this AU and BP. Okay. Somebody says false, and if somebody will say false, then he or she has to give some counter example, and if somebody says it's true, then he or she has to give some proof. I'm not giving you the answer. And if
Sir,
you do, yes.
sir, 3 into 2
Okay, somebody says 3 into 2
minus 2 into 2
minus 2 into 2 equal to 2.
equal to 2.
Yes.
But here, sir, GCD of 3 and 2 is not equal to 2. It will be 1.
Okay. So here GCD of 2 and 3 equal to 1, but not true. Okay. But not, sorry, not true, no, not 2. So if you are able to, it's okay. So the question is, if I now, what is the exact inverse of this? But you can see that 2 and 2, if I consider GCD of 2 and minus 2, say, or maybe 2 and 2, then that is true. Okay. So what is the inverse of this? So converse of this. So here you are given A and B, given A and B, right? Not both zero. And there are some integers or maybe positive integer, or doesn't matter. So what would be the converse of this? If D equal to AU plus BV for some U and V for the given AB, note that A and B are given. So in the converse one, the idea was will be also A and B are given. A and B are given, and the idea is not both of them are zero. Okay. Now, if there exists UV belongs to Z such that D equal to AU plus BV, okay, then will D be the GCD of GCD of A and B. So just have a look at your statement, what you did, nicely prepared. It's a very good observation. Just have a look at whether this is true or false, whether this is actually working for your case or not. If it works is fine. If not, then again you have to find something. Okay. So
Said,
yeah, please.
said if I take 3 into 2 minus 2 into 1 equals to 4.
Sorry. What is your AB?
Said C 1.
Yes. So A equal to 3, B equal to 1,
Said C into 2
3 into 2
minus 2 into 1
minus 2 into 1
equals to 4.
equal to 4. Okay.
The GCD of AB not equals to 4.
GCD of AB not equal to 4. Very good. So almost similar example like this. Okay. So as I just now mentioned is the converse. So why I am saying the converse you also need to have a look at, because the converse statements are also very important for competitive exams. So in case of a competitive exam, you will sometimes have to answer for multiple correct choice answers. So it would be a multiple choice answer. Okay. And sometimes it happens that you get confused when you get the converse of some known statement. So that's why it's very important that you should have a look at the converse of every statement. What would be the converse, how it look like? Then it will be helpful during your exam time when you will get some multiple choice answer. So you need to pick up one from them, or many of them may be correct. Out of the four options, you may find some of the exams they are conducted in such a way that out of say four options, maybe more than one options are correct. Okay. In that case, the converse of some statements plays an important role, because you can understand that if you are one of the paper setters, then how will you choose your, or how will you make your paper in such a way that more than one statement would be correct? You suddenly not will find some statement from one statement from complex analysis, one statement from real analysis, one statement from linear algebra, another statement is from abstract algebra. That should not be the case. The case should be like, you should ask a question on a same topic, maybe on a same statement. And when you are going to have some multiple choice, usually the paper setter, they sometimes prefer to give a converse of the some statement, but in some ambiguous way, so that you get little bit of confused. Okay. So if you are little bit of confused, then you might lose the answer. So that's why you have to be little careful enough, and sometimes I will ask you some of the very simple converse statement of some theorem or something, then you will have to give me the proper answer without any kind of hesitation. Okay. So now it's clear to all of you. Okay. So let's come to the actual formula. So this is my formula and I want to attack this. I want to attack this problem. Okay. So here the group is my S2, sorry, S101, and element was the cycle 1 to 50. And now if I ask you the question, what is the order of this element? What is the order of this element?
50.
50.
Very good. As I mentioned, if it is only a single cycle, then the length of the cycle would be the order of the element. So as I mentioned in my earlier classes, now what I'm going to show, I want to find the order of the element 1, 2, 3, 50 to the power 8. Now what would be this? Just now we have mentioned, so it will be 50 divided by GCD of, so this is my T, and if you look at this formula, then what it says, this should be order of A. So A to the power T, order of A divided by GCD of order of A comma T. So GCD of, then order of A was here, this is my A, so order of A was 50 comma 8. Okay, so that means 50 divided by, what is the GCD of 50 and 8? What is the GCD?
2.
2, 25. Is it clear to all of you? Is it clear to all of you? Any question or any ambiguity if you have, please let me know. So now your homework is to prove this statement from any book. So it's also available in my book as well. So you can consider any other book. So this is your homework. Okay. So now it's fine. Okay. Very good. So now let's come to the other point, other problem. Yeah. So I will come to it maybe after some words. Okay. Okay. Let's come to problem number 3. Let G be a finite group whose order is not divisible by 3. Show that for every G belongs to G, there exists an element H belongs to G such that G equal to HQ. Many of you had, I have seen that many of you had already done this problem. So this is my question number 3. Okay. So what it says that, so order of the group is not a multiple of 3. So what it says, the is not divisible by 3. Then how it should look like? It should look like either 3k plus 1 or 3k plus 2. So what you need to show, it is given that the order of G is finite and it's not a multiple of 3. So if it is not a multiple of 3, so any number, if I write any number, then this number might either of the form 3k or 3k plus 1 or 3k plus 2. That's very standard way of writing. I can write it in terms of 4 as well. So any number is either of this form 4k or 4k plus 1 or 4k plus 2 or 4k plus 3. I can also write it in terms of 5. In that case, 5k, 5k plus 1, 5k plus 2, 5k plus 3, 5k plus 4, and so on. So here it's given not a multiple of 3, so 3 could be my keyword. So it cannot be of this form, so we are remaining with this form. So order of G either of 3k plus 1 or 3k plus 2 form. Okay. Then what it says, it says that show that for every G there exists an element H such that G equal to HQ. Okay. So first let order of G equal to 3k plus 1. Take any G, let G belongs to G. Then if we know that if we have put the element and its order, so this is the order of the group, and if we have the power till the order of the group, what it will happen? What it will be? If I take any element and if I compose it till the order of the group, then what will happen? What should I write here? This should be E. So it's again a result. So let G be a finite group of order n, then for all A belongs to G, A to the power n is always E. So this result, if you have not yet done, you must do this. Mind that this is a finite group of order n. So if you just multiply or doing the composition in many times, then that will certainly be the identity element E. So here this is the order of the group. As a result, when you are composing G this many times, that becomes E. So if you can multiply both sides with respect to G inverse, then what I will get? I'll get G inverse into G to the power 3k plus 1 equal to G inverse. That implies G to the power 3k equal to G inverse. Okay. Now what you need to show? You need to show that for every G there exists some element H such that G equal to HK. Okay. So other way around, what I can do is that instead of doing this, so I need G actually. So I did a mistake here, or I could have done one more step. So that should be a multiple of 3, right? So if I do like if I multiply both sides with G, what will get? You will get here G, but here it won't be your G. So one thing you can do that from here also, you can do that. What you will do, you will just multiply both sides with say G square, or so this is your G square. What I am saying that instead of this, you just make it G. So G will be G to the power 3k whole inverse, right? If I make an inverse over this, I can make an inverse over both sides. And what is the G inverse of inverse? That becomes G. And what is the G 3 to the power k inverse? That is G of minus 3k. And you can consider this to be as minus of k to the power of 3, and you can consider this to be as h and then h cube. Is it clear to all of you? Is this clear to all of you? So we had G inverse, and then what I am doing again inverse on both sides. Then we get this inverse of G inverse of inverse, that becomes G, and that becomes this. So for this G, I have some H. What is H here? So H equal to G to the power of minus K, such that G equal to H cube. That's what we need to prove. G equal to H cube. Similarly, you need to then check what would be your, if this is your 3k plus 2. If order of G is 3k plus 2. Is it clear to all of you? Any question or query? If you have, please let me know. Is it clear? Okay. Well, then let's come to question number 4. Give an example of an finite group G such that every subgroup of G is cyclic. So give an example of an infinite group G such that every subgroup of G is cyclic. Okay. So what we need to show? We need to have a group itself G which is infinite. But every subgroup of G, every subgroup of G is cyclic. So if I consider Z G to be my Z, then every subgroup, if I consider any subgroup of this, then it must be of the form NZ. So that is again a result. So you need to prove this result. This is also your homework, which says that any subgroup of Z plus is of the form. nz, where n equal to 0, 1, 2, dot, dot, dot. So if I consider any subgroup, say h of z, then the form of h is of this form nz. So it may be 2z, it may be 3z. If it is n equal to 0, then it will become this. If n equal to 1, then this. So they are the trivial subgroup of Z. But other than them, other than any subgroup of which are different from these two are uh, non-trivial subgroups. Non-trivial subgroups. In my last class, I have already mentioned about this. And who are the proper subgroups? Except for this, all subgroups are proper subgroups of Z. Proper subgroups. Okay. So here you can understand that Z itself is a cyclic group. As a result, the statement is true. Here I have given what is, so you have to be careful about each and every word. Give an example of an infinite group such that every subgroup of G is cyclic. Every subgroup of G includes G itself. I have not mentioned about every proper subgroup of G. If I could have given this proper subgroup, then you should not consider G itself. But in that case also, if I give an example of an infinite group G such that every proper subgroup of G is cyclic, then also your this example will do. But now I am giving another question. It's again very important from competitive exam of view. Give an example, give an example of an infinite non-cyclic group. Mind that this is I have introducing something else. Non-cyclic group such that every proper subgroup of G is cyclic. And this is very important. Here, if I miss this term, every proper, instead of every proper, if I just write every subgroup of G is cyclic, then there will be a problem in question, because if I drop this proper, then G will be a subgroup of G itself. And I want, so initially my G was non-cyclic, but I want a cyclic. So that would be a confusion or contradiction. As a result, that will be a erroneous question. But now it's fine. Give an example of an infinite non-cyclic group such that every proper subgroup of G is cyclic. Can you tell me such example? Can you tell me one such
Sir,
example? Sorry?
sir G, sir, sir take G as circle group, মানে S1,
Okay.
and the subgroups of G will be n root of unity.
Okay, just a minute. So your G is S1. That means, as I mentioned in my previous classes, I have already explained what is S1. So S1 is in the complex plane. So mostly sister non-zero complex number. It's a subgroup of non-zero complex number, and it's all points on this circle whose radius is 1. So any point here should look like e to the power I theta. Okay. Now what is your so you say that your G is S1, right? And you say,
Yes,
what do you
and
say? Yeah, what do you say?
and subgroups are n root of unity.
Okay, subgroups are, you say that nth root of unity. Let's see, nth roots of unity. So nth roots of unity, what it should contain, what, how many elements? 1, some omega, omega square, omega to the power n minus 1, right? And you say that omega n equal to 1, and this is the smallest. That's what you want to say, right?
Yes, sir.
So my question is, after your answer, my question is there any subgroup of S1 other than if I call it nth root of unity, if I call it Hn, other than Hn? So Hn is a finite subgroup of S1, no doubt about this. My question is there any subgroup of S1 other than Hn? What will be your answer? What do you think, or what anybody will think? But he has gone to up to a very certain portion, and that's very important. So very good intuition, I must appreciate this. But if you are able to show that there exists no, in case of Z, what we have seen that all the subgroups, mind that all the subgroups must look like this, and all the subgroups, and so that is generated by n. As a result, you can say that all subgroups of Z are cyclic. It's fine. But if you say that there is no doubt that Hn is a subgroup of S1 for all n, whatever be the n you take from greater than equal to 1, for all n, so there are infinitely many such subgroups, no doubt about that. Now the question is S1 contains only this type of subgroups or any other type of subgroups? It may happen that S1 contains some subgroup S such that S is not cyclic. Might happen. Then your result S1 will not be the actual answer, because in S1, if I am able to find such S which is not cyclic, then your answer would be wrong, right? But you say that your answer is correct. That means all the subgroups of S1 must look like this for some n. That means you want to say that all subgroups of S1 are finite. Is it true? His From his derivation, it follows that any subgroup of S1 is finite. Now the question is it true or false? What do you think? Can you give me
Sir, it
some
is false
infi?
actually.
Okay, why?
So actually, if I take e to the power some x, and if x is irrational, then the cyclic, then this is not cyclic, and this is infinite group.
Okay, what he says that he has taken some h of this form e to the power I theta, such that theta theta is an irrational number, or you want to vary theta over irrational numbers. What is your argument?
So theta is an irrational number.
If theta is an irrational number, then how many elements are there in H?
Sir, infinitely many.
Okay. Theta is an irrational number, means theta is a fixed irrational number, you want to say, right? Say root 2. So if
Root
that is
2,
the,
root 3. Root 3 or should also be there.
that means you are actually varying theta over irrational numbers. That's what
Yes,
you
sir.
want to say.
Yes, sir.
Okay.
Yes.
So it should not be like this. Then that means this belongs to the set of all irrational numbers. If I write like this, irrational number, set of all irrational numbers. That is your set. Now the question is it a group or is it a subgroup? What would be the identity element of this? Tell me. what would be the identity element of H if you vary theta among all irrational numbers? What would be the identity element for this H? So you have constructed a set, no doubt. Now tell me what would be the identity element of H. So its elements should look like e to the power I root 2, e to the power I root 3, e to the power I root 5, say e to the power minus I root 5 and so on, right? Now tell me, is 1, that is e to the power I into 0, an element of H?
No, sir.
Yes or no?
No, sir.
So it's not in H. But you are saying that S1 has the identity element 1. And if H to be a subgroup of S1, then it must contain the same identity element. But just now, the way that you have defined the subgroup or subset, not a subgroup, the way that you have defined the subset is not contained, I mean, one is not contained within this H. As a result, H can never be a subgroup of S1. So the H that you have just now constructed, but it was really a very good try. Very good try. So H is not a,
Sir, H, if I call H union one, it should be a subgroup.
okay, let's see. If I consider H union 1, okay, according to him, it will be a subgroup. Uh, will all of you will agree with that? So, okay, first let me know, first check if H is a subgroup or not. So, if I consider without that at the initial phase, without considering having the union 1 with this H is not a subgroup of S1. Very good. But now he has introduced say H1 equal to H union 1. Now my question is, or he believes that H1 is a subgroup of S1. True or false? What do you think? What is your answer? True or false? Anybody? So he has given a very nice observation. That's very good. What is your answer? True or false? So if you say it's true, then you need to show that this is a subgroup. And if you say it's false, you need to give some point or some counter example or some justification. Just like here, I have shown that one is not within H. Okay. What are the guess for others?
Sir, false.
Okay. Why?
Sir, if you take e to the power I root 2
Yes.
and e to the power I minus root 2,
E to the power I minus root 2.
I mean
What does
minus
it
I root
mean?
2, minus I root
Okay.
2.
Okay.
Sir, if we multiply them, then it must be not in that.
Why not? It's what is the multiplication? E to the power I root 2
Minus.
minus I root 2. And that becomes e to the power 0 and that is 1.
Sir, does not.
1 is already there. He has included 1.
Oh, sir, huh. Yes, sir. Uh,
Then what would be your conclusion? Then what would be your conclusion? What is your conclusion then? Okay,
True, sir.
okay.
So
So
it's
now give me a proof for that. How you will able to prove that this is a subgroup? How will you prove? And if so, is this a cyclic group? So okay, so assume that.
No, sir, it is not a cyclic group.
Okay, so is it a subgroup of S1? My first question. Question number two, if H1 is a subgroup of S1, will it be a cyclic subgroup of S1? If this is not a cyclic subgroup of S1, then we started with some point where he has given some example that nth root of unity will not be sufficient for us. Then we find that S1 contains a subgroup which is not cyclic. Okay, then that would be a problem. So that will lead to some other problem. Okay, now somebody explain me how to prove that H1 is a subgroup of S1. So how to prove that H1 is a subgroup of S1, or how to disprove H1 is a subgroup of S1? I will keep both the argument open. Those who think that H1 is really a subgroup of S1, for them, they need to prove, and those who think that it's really not a subgroup of S1, they must give me some counter example or some extra logic so that I will be convinced enough to give you the decision that, okay, that's not a subgroup. It's quite interesting, actually. And this groups are really very interesting. Okay, suppose H1 is a cyclic, suppose H1 is a subgroup of S1. Suppose I have assumed or I have proved by some means. Now, is this correct? Is
Sir,
it a
sir, sir.
cyclic subgroup? Yes.
Sir, actually, if I take e to the power I root 3 and e to the power I root 27,
E to the power I root 27. Okay.
I root 3 and e to the power I root 27.
Okay. E to the power I root 3 and e to the power I, you want to take 3 root 3, right?
Hmm.
27 is 3 root 3. Yeah.
Sir, sorry.
They will be added, not okay. Okay, but anyway, so it's
Sir, if
uh,
x and y are irrational, then x plus y should be irrational.
not necessarily. If you take x equal to y, x equal to minus, say y equal to minus x, then that becomes 0. So your x
Sir,
and y equal to minus x, then x plus y becomes 0. That is rational. This is irrational. This is irrational.
sir, then zero is actually present there.
0 is present there where?
Uh, some
So all the things are happening on the exponent. Mind that. And that makes you e to the power 0 equal to 1. Clear? Okay.
sir,
Yeah. Tell me.
sir, if it is e to the power I into root 2 plus 1 and
E to the power
I
I
into root 2 plus 1
root 2 plus 1. Very good.
and e to the power I into minus root 2, then it
E
is
to the
coming
power
to,
I into, so this one.
yes.
root 2. Okay, and if you
Then,
multiply them,
then we'll get e to the power I, which isn't a irrational number.
then will that be a closure property will satisfy? Then e to the power I root 2 plus I minus I root 2, and that becomes e to the power I.
Yes,
Okay, in
No,
that
sir,
case, the
it is not a group actually. I mean, not a subgroup.
it's not a
yes,
subgroup. Then.
हाँ
very
yes,
very, now
असाधारण
you get,
असाधारण
now you get this answer. Okay, so it's not even a group because the closure property does not satisfy here. So even if you, but it was a very good try. That's what the, when you are going to study any subject, you should do on your own. Start with some question and then start developing things. But if you read the book directly, then suddenly you will get the actual answer. And that way I don't want. I want to, you should develop your own thinking. That's most important. Anyway, but it was a really a very good try and a very nice try, that you have already developed the idea that okay, you are trying to, you started with the set H, then you tried to add something on it. Initially you started to add one on it, and apparently it looked like it was almost a group. H1 was like a group, and you were almost convinced that it could be a group. And then if you are convinced enough, then I was thinking of sending you to some other things. You got the answer quite easily, but otherwise I could have taken you to, you might have concluded that that would be a cyclic subgroup, and ultimately will arrive that uh, it will not be a cyclic subgroup, but ultimately you will arrive that it is not even a group, but you are doing too many things. That's why the major problem for most of us is that when we think things, we know many things, but not everything is very much clear from our heart. So we may develop many things at a very high level, but if you go little back and if you ask the questions from the very basics, you will be stuck. So you might be thinking about whether this is a cyclic subgroup or not, but actually this is not a group. But this example should have come to you little earlier, but yes, anyway, within that class it came. That's why I kept both the debate open to all of you. It's true and false. I have not closed the yet, so otherwise I could have given it to your homework, and I thought that maybe in the next class, but thanks that you have already came up with an example. Okay, so till now his answer is almost right? So not yet you have found any of the subgroups which are infinite in nature and which is not cyclic. Okay, till now, those who claimed that any subgroup of this, of almost of this form, because you said false, but not yet you came up with any such nice example, so that you will able to construct or give any argument against his statement. Okay, let us try to have some kind of other kind of. So let's start with say 2 to the power n. H of 2 to the power n is all such z belongs to non-zero complex number such that z to the power z 2 to the power n equal to 1. That means I am considering the, he was considering the nth root of unity, but now I am considering 2 to the power nth root of unity. Okay, so how many elements does it have? What is the order of this group? So of course we have seen that this is a cyclic group because it's the, he considered nth root of unity, and I, instead of n, I just consider 2 to the power nth root of unity. Suppose he has considered third root of unity and I am considering 2 to the power 3. That means eighth root of unity. So as a whole, it actually the same. So it's kind of nth root of unity. So what is the order of this group? What is the order of this group?
So 2 to
Quickly.
the power n.
To
Yes,
the
2 to
power
the
n.
power n. So nth root of unity contains n elements. So 2 to the power nth root of unity will suddenly contain 2 to the power n. And most importantly, this is a cyclic group, right? Cyclic group. and it is generated by the nth root of unit, 2 to the power nth root of unity. Like in case of 1 omega omega square, omega was my generator. Similarly here, if 1 omega omega square up to omega to the power 2 to the power n minus 1, then suddenly this omega will be my generator. How it satisfies? So omega to the power n is equal to 1, and 2 to the power n is the smallest integer for which omega 2 to the power 2 to the power omega 2 to the power 2 to the power n equal to 1. That's why the order of the element as well as the order of the group is same, and as a result it could be a generator. Okay, now if I make a simple twist, let H is my group, and if I consider like this, all such Z belongs to C star such that Z of 2 to the power n equal to 1, but I just make a twist here over here like this, where n starts from 0, 1, 2, and so on. Okay, see, so here n was my natural number in that h 2 to the power n that was fixed, right? But now I am considering all such. For example, here what I am considering H, if I consider, then it Z belongs to C star such that if I put Z to the power n, if I put n value to be 0, then 2 to the power 0 means 1, so it's 1. Also I am considering n to be 1, then all such Z such that Z 2 to the power 1 equal to 1. All such Z such that 2 square equal to 1. All such Z such that 2 to the power 2 to the power cube is 1, and so on. So infinitely many number of elements are there. So what we need to prove is that we need to prove that this is a set now. Now whether this set is a subgroup or not, that we need to first prove. Okay, so this is no doubt a subset of S1. Is it clear to all of you? Is this group a subset of S1? What do you think? Is this group a subset of S1? So geometrically, if I draw like this, geometrically how it looks like, then it will be clear for all of you how it's a subset of S1. So, sorry. Okay, so this is my S1 with R equal to 1. What it says, it contains Z equal Z to the power 1, Z equal to 1 means this point is there. Okay, it says that Z2 equal to 1. That means what are the elements Z here? 1 and minus 1. That means plus minus 1. Z square equal to 1 means Z equal to plus minus 1. This means this point is also here. Z4 equal to 1. That means 1 I minus 1 minus I. The 4 points are there. Then Z cube, Z to the power 8 is there. Then you can understand that you can just subdivide this point, this point, this point, and this point will also be there. That means 1, 2, 3, 4, 5, 6, 7, and 8. 8 points will be there. But as you understand that if I go on doing this, Z to the power 2n equal to 1, then n 2 to the power n many points are there, but all the points will be within S1. You cannot go out of S1. Okay, so set wise, this H is suddenly a subset of H, no doubt about that. This set is no doubt that is a subset of S1. Okay, now the question is it a subgroup of S1? question. Is H a subgroup of S1? What is your intuition? What is your intuition? True or false? What is your intuition? True or false? What do you think? Are you clear about the set H? So it contains it in varies, right? In varies. That means it's infinite. So it's going on, keep on going on, going on, going on, but still within S1. But again, if I consider again 16, if 2 to the power 4 equal to 1, then again some more extra points will join and so on. But still, you cannot go out of S1. My question is S1, is this H a subgroup of S1 or not? It's a subset, there is no doubt about that. But the question is it a subgroup or not? What do you think?
Sir,
So take
true.
in what? Sorry, what do you think?
Sir, true. It's
Yes,
subgroup of S.
S1. So what I need to show that claim H is a subgroup of S1. So first thing is that H is a subset of S1. I think it's clear to all of you. Is it clear? Because if you draw
Yes,
it,
sir.
then it will be clear. Second part, we need to show that let AB belongs to H. To show A B inverse will also belongs to H. If we are able to prove that, then we are basically done to show that H is a subgroup of S1. Okay. So as A belongs to H, there exists some N1 belongs to 0, 1, 2, such that A to the power 2 to the power N1 equal to 1. Okay. Similarly, as B belongs to H, there exists N2 belongs to 0, 1, 2, such that A to the power 2 to the power N2 equal to 1. For example, side by
Sir,
side, if I,
B to the power.
sorry, yeah, it would be B to the power. Thank you. So for example, side by side, you can think in that way. That will help you in understanding this thing. Say N1 equal to say 2 and N2 equal to say say 3. Okay. Now, if you look at the construction in this particular construction, so that means this is your 2, that means N2 square equal to 1. That means you have basically these points. Okay, so let me first make it in black. 4 points. And when you have this to be 3, then you have basically 8 points, 2 to the power 3. That means B to the power 2 to the power 3. That means B to the power 8 equal to 1. So how many elements? 8 elements. Who are they? So they are this element along with this element, along with this element, along with this, 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 this. Okay. Now you see that if the value of N2 is greater than N1, what is happening? All the portions that were already happened for N2 2 is already there in N1. So they are already included. So they were for N1, and when I consider for N2, and if the value of N2 is more than N1, then suddenly these previous values will also be considered. See, they are the extra points, but it also includes the previous one. So if the value of N2 is more than that of the N1, then suddenly all the points that are encountered for N1 will also be encountered for N2. Is this statement clear to all of you? Is this statement clear to all of you?
Yes,
Because
sir.
for example, okay, so for n equal to 3, the 8 points, and for n equal to 2 it's 4 points, but these 4 points are already included for these 8 points. That means if n2 is greater than n1, then suddenly all the previous points will be included. Now what I need to show? To show A B inverse belongs to H, we need to show there exists some n belongs to 0, 1, 2, such that A B inverse 2 to the power 2n equal to 1. If we are able to show this, then we are done basically, right? Now tell me this question, what could be your n? So you have already n1 and n2, okay? Now, for example, I have taken this. In that case, A could be of this 4 points, and if n2 equal to 3, then the 8 points will be this. Now you take any two elements, A and then B inverse, okay? So among this, suppose you have taken A from here, and for B also, when we are considering B, note that my n2 is more, right? So B will have more points, and all the points of B is already, all the points of A are already included in B because n2 is more, right? So when I am considering A B inverse, that means A is already considered while discussing about all the points of B. So A B inverse means nothing but among all the A and B inverse. So as just now we have mentioned, since n2 is bigger than n1, so this whole inverse will also be an element because that is a subgroup, and that is the eighth root of unity for n2, for B is n2, and that is for eighth root of unity, okay, and that contains all the fourth root of unity. Now when I consider A from fourth root of unity and B from eighth root of unity, that means A is already considered in eighth root of unity. And when, since eighth root of unity is a subgroup of S1, that means A B inverse is already within eighth root of unity. As a result, eighth root of unity is already there. And if I consider eighth root of unity over 2 to the power n2, that means 3, then that will become 1. So I can think of this n to be my maximum of n1 and n2. Then we are done basically. If I consider maximum of n1 and n2, then we are done. Then that n will help us in getting the answer that will help us. For example, in this case, if I consider n to be n1 to be 2 and n2 to be 3, then if I consider 3, then say A. So how many elements are there in for A? A are basically, so A belongs to which set? 1, then I, minus 1, minus I, right? And what are the set of B? It 8 elements. That means say 1, omega, omega square, up to omega to the power 7. But as just now I have mentioned, some of this, for example, 1 is like this, and some of this I must be somewhere here, minus 1 will also somewhere here, minus I will somewhere here within this. So if I consider now A B inverse, and if I consider A B inverse to the power 2 cube as my n2 is 3, which is the maximum of 2 and 3, then suddenly, since A is already considered here, then A B inverse will also belongs to some of these elements. And since we are making it to the power 8, already we know that anything to the power 8 will give me one value. So if I consider n to be the maximum of n1 comma n2, then that will be fine for us. Just now I just mentioned if n to be n1 into n2, that will also be done. If I consider n1 plus n2, that will also be done. So anything more than that, so it's sufficient to take n to be maximum of n1 comma n2, and that will give you the answer. Is it clear to all of you? Now is it clear? Any question? Any question yet? Okay. So I assume that it's clear. Okay. So what we see that we find a subgroup H which is a subgroup of S1. Now my question is H a cyclic group? Question. Is H a cyclic group? What is your intuition? True or false? Okay. So what you can see is that H is basically union of H of 2 to the power 0, H of 2 to the power 1, H of 2 square, union, and so on. That you can see, it's endless. So 2 to the power cube, 2 to the power 4, and so on. H is the union of, it contains all the points of from this set, but it's an union of all those things, right? Now, if you think that it's a cyclic group, if this is, so the answer will be false. If you think that it's a cyclic group, then it must be generated by some single element, okay? And that single element will certainly belongs to some of this, somewhere it will belong. And if it belongs to some of this subgroup, then what will happen for the other groups which are bigger than this? Then this element will not be able to generate the elements which are from the bigger groups, bigger subgroups, H to the power. Suppose the generator, so the generator, suppose G has a generator, say G is the generator of H, then suddenly G will belong to some of the, there must exist some n such that G belongs to H of 2 to the power n. Now what will happen for H of 2 to the power n plus 1? Will that G be able to generate all such elements? Because it will not have power. For example, if I consider this, it will have no ability to, so I is a generator for this group, no doubt about that. But will that I be able to generate all the elements from here? No, it can generate only 4 elements from here. But remaining 4 elements, it will not be able to generate. So similarly here also, if G belongs to this, G will certainly be able to generate all the elements from here, but it will not certainly have the ability to generate elements from here. So as a result, you cannot be able to say that H is a cyclic group. So what we get? We get S1. We get S1 as an infinite group. So S1 is an infinite group. But S1 contains a subgroup H which is of the form all such Z belongs to C star such that Z 2 to the power n equal to 1 where n varies 0, 1, 2 contains a subgroup H which is not cyclic. So this group is very important. Now I think the question from where we started, the person who has given me the answer that S1 could be your answer is not correct. Okay. So I think it's today we have done a lot of things, but please have a look at this video once again and then try to clarify on yourself whatever I told is what you understand or not. But in my next class, I will show that this H will serve our purpose. So this H is a group. So itself. So this is not a cyclic group. Just now we have shown. So this H is not a cyclic group, but every every proper subgroup of H is cyclic. That is quite interesting, and in many of the examinations you will find this question in different forms. So this gives an example where the original group is not cyclic, but every proper subgroup of H is cyclic, and that's very important. And this example is very rare. You won't be able to find many of the other examples which satisfy this property. So this is quite important. So today I will stop here. So if you have any question, please let me know.